All right, so let's get started. The goal for this video is to provide a sort of comprehensive review exercise as we are nearing the end of this course. So we are going to implement together a linked list. We are going to implement it in a different way than what you have seen in your reading assignment. Okay, so this is going to be a complementary, supplementary, approach that is going to add something to your reading assignment. The goal in the differences that we are going to focus on is to kind of like illustrate, application of the things that we have been studying lately, like for example, pointers, dynamic memory allocation, of course, but also more specifically, we're going to stretch it a little bit and go up to pointers on pointers so that you have like a strong case study pretty much with this implementation that helps you prepare for the final exam. So let's jump in the code. I have a layout here that is it's a very classic layout with one exception. So I have a Linky. Linky is going to be the name of our linked list application. So linky-test.c. This is where we are going to have our main. So we are going to include linky.h, which is going to have our function prototypes, and it's going to also have the data structure definition, okay? And then I'm going to provide my main here, int main. Here we are, return, exit, success, the usual stuff, okay? And I'm going to leave it at that for now. And then to be able to use exit success, I'm going to have include std lib.h. And I'm going to also include, just because I'm probably going to need it at some point, stdio.h, okay? And stdbool will wait to see if we use booleans at all in this file or something like that. So going to save that. Let's GCC it. Make sure that we don't have any typo. Linky test.c. Here we are. So that's going to be my first file, okay? And this is going to be where I'm going to use all of the functions that I'm going to define in our little linked list library, okay, to test them. Then linky.h. Linky.h is going to be the header file for that little linked list library. So I'm going to have the usual pragma once to make sure that if I somehow manage to multiple times include linky.h, right, it's going to automatically manage it for me so that I don't have like double declaration and stuff like that. And what I'm going to do inside of here, I'm going to define my data structure. I'm going to define my data structure, and I'm going to put the prototype of all my functions. So we're going to do it a little bit at a time, okay? So the data structure, we're going to call it a node, okay? There's going to be, a linked list is going to be composed of multiple nodes, each linked to the previous one. So just to illustrate that quickly, let me grab a pen. This is what we want, right? We want to be able to have a pointer P, for example, that's going to point to one of those node structures. The node structure is going to have two components. The first one is going to be called the data, which is going to be the value, an int, for example, that it's carrying. And then the next component is going to be, well, appropriately called next. It's going to be a pointer that's going to refer to the next element in the linked list. That's why they are called a linked list, okay? And we are going to keep having like pointers like that on the next element, okay? All of those double boxes are of the same data type, node, okay? And we are going to have pointer like that until we have a null here. And then that means, we don't have anything left in the linked list. So the thing with linked list is that the pointer here, P, points to the head of the list, but I could have another pointer P2 that would just point to this element. And from the perspective of the definition of a linked list, both P and P2 point to a linked list, okay? P could point to the entire linked list. P2 points to the linked list starting with the item carrying the value 23 and up to the end of the linked list. It's the same thing that we've seen with pointer on character as used for strings, okay? You have a pointer on character, it points to the first character of a string, congratulations, you have a pointer to a string. But if you make another pointer point to a character in the middle of the string, so here's a string, for example, okay? So it's exactly the same thing. If I have a pointer 1 that points here, the first character, then it points to the entire string up to the \0 character at the end. But I can have a pointer P2 that's going to point here, a pointer P3 that's going to point here, and all of those pointers can be used as strings. They all refer to the same string or component of the original string, right? But they are all the address of a character, and that character is followed by another character, another character, another character, up to the end of string marker. Same logic here for linked list. A pointer to a node is going to refer to the head of that list, which is going to refer to the next head of the sublist that comes after, the remainder, if you will, and so on and so forth. So having a pointer to any node element gives you a linked list as well. All right, so now that this is out of the way, how do we define our data structure? So we're going to use structs. Okay, this is the main thing that we are going to use to define almost all data structures in the C programming language. So I want to define a struct, and I'm going to call it node underscore s, s for struct. So there are many different, how to say, not standard, but conventions that can be used here, okay? I'm going to always start with an uppercase, the name of a struct data type, and I'm going to follow by an underscore s when it's the name, the tag name for the structure, okay? So struct node s, and I'm going to define it. What do I want inside this struct node s? I want some data, so I'm going to go with something simple. We're just going to carry an int data, okay? And then I want a pointer named next, and that pointer is going to be a pointer on an element of type as well, struct node underscore s, okay? So struct node underscore s, this is a pointer next. Okay, so I use struct node underscore s as the name of the new data type that I'm defining here, the new structure that I'm defining here. Okay, it's because I don't have a choice yet. I haven't had a chance to do a type def. Okay, so but that works. I can do this, and I'm going to GCC. Let's see if I compile this. It's going to include the .h, so that's going to compile also the content of the .h indirectly. So you can see that it's compiling okay. I have my data structure, it makes sense, but I would like something a little bit more convenient than having to write always struct node s as the name of the data type. For example, if I am in the main, if I want to do a struct node underscore s pointer, and this is going to be my first linked list, L1 equal null, okay? Instead of having to write this, which is perfectly fine, okay? We can write it like that, it's just long. Instead of writing things like this, what I would like to be able to do is type def a new data type that I'm going to call node, and say, for example, I want a node pointer L1 set originally to null, okay? So to be able to do that, the node data type doesn't exist yet. So we are going to define it also in linky.h. And we are going to define it using type def. So the type def is going to say that a struct node underscore s, okay, is going to be referred to as the data type node. Once we have that integrated, there we go, it's going to compile again. All right, so now I can declare a pointer on a node. So a pointer on a node is one of, oops, I cannot do that. There we go. One of those guys. This is a pointer on a node. Okay, so it's not technically part of our linked list. Okay, except that the data type of those variables that we're going to use to point to a linked list, like P, P2, etc., the same data type is going to be used here for the field next inside the data structure. Okay, after all, if you look at the definition, this is a pointer on a struct node s, and when I define L1 here, it's also a node, a pointer on node, which is a pointer on a struct node underscore s. Okay, so the same data type is used in both cases here. So I want to be able to define those things. I have my type def. I have my my main that is not creating a node, but defining a pointer on the node, my next step is I want to be able to say, you know, I need a new node. So I'm going to have a method called node, and we are going to call it node create. Okay. And I'm going to pass to this node create some value. Like, for example, I want to create a node that holds the value 42. And it's going to return to me the address, the pointer on a newly allocated struct node underscore s, or a newly allocated node, okay, for short, that is going to contain the value 42, and that is going to have a next field set to null. Okay, meaning I'm just a standalone node, you know, there's no other node linked after me. When you create a new node, that's going to be the default. It has some value inside of it, but it doesn't have a pointer to another node. It's not yet linked into a list or something like that, okay? So this is the first function that we are going to actually work on together. So let me save this, go back to linky.h, and now I'm going to start listing the prototype of my function. So node star node create int value. Okay? And I don't have to put the name of the parameter, but I'm going to put it because it kind of self-documents, you know, that when you create a node, you're going to pass the value that you want this node to carry along, okay? And this function is going to return a pointer on the new node. So let's save that. Let's go to linky.c, and then in linky.c, we are going to include linky.h, and we are going to implement all of our method. Okay, so let's go to the first one, the create method. It's going to be relatively easy, right? It's a matter of doing a malloc. So what I'm going to do here is I'm going to say, all right, I need a node pointer that I'm going to call TMP, okay, just to highlight the fact that it's temporary. I'm going to initialize it to null because I like to write clean code. And I'm trying to show you how to write clean code, so this is why I forced myself to initialize it to null, of course. So my pointer TMP is set to null right now. I'm going to say TMP equal, so I want to allocate dynamically. What do I want to allocate? I want to allocate a node structure, or a struct node underscore s, okay? So size of, and I could write here struct node underscore s, or more simply, because I have a type def, you know, let's use it, size of node, okay? So I want to allocate one new node. And of course, I'm going to return a pointer that is going to be, in the case of malloc, a void star, a pointer on void. So I want to convert that to a node star, okay? Which is the data type of my variable TMP, which is the data type that I want to eventually return from my function. So at the end of my function, for sure, I'm going to say return, TMP, okay? And now I need to populate information inside that node. So TMP, I'm going to use the arrow notation because I have a pointer on a struct, okay? TMP arrow data equal the value that you gave me. TMP arrow next equal, well, okay, standalone, I'm creating one node, it's standalone, it's not linked to anything else, so the next pointer is going to be null. And that's pretty much it. Okay, I have here like everything I need to create one single node. So let's give it a shot. Let's compile. And it's telling me that there is an undefined reference to something called node create. Yes, it's because I have it in the .h, but I didn't compile actually linky.c. So let's remedy that situation. And a lot of other problems. So the other problem comes from the fact that in linky.c I use things like null, etc., and I should have like some standard library includes that I'm missing. So you know what? Instead of putting them here, actually no, yeah, you know what? I should just put them here. Found include, and I'm going to say stdlib.h. Do I do any printf? Not yet. So let's start with this one, and we're going to recompile here. And there we go. stdlib.h took care of a definition of null, all of those things, by including over header files as well. So, can I test this? Well, I can definitely run it. But how am I going to know that it's working? I'm going to do a printf, and I'm going to display %t followed by %p. Okay, I'm not trying to make the display fancy here. I just want to quickly display what the node contains, and then I will remove that printf. Okay, so L1, and I don't know why I uppercased L1 here. Let's call it P1 because the lowercase l and the 1 are kind of like really similar. So there we go. P1 arrow, that's going to be data. P1 arrow next. I just want to make sure that there is, the value 42 that I have here, and the value null for the next pointer in there. Save this. GCC. Well, for the first time, we're going to run our code, and it's telling me that I have the value 42 and the pointer nil, which is something as null, okay, inside that that cell. So that's it. I have a way to create independent nodes. Now, what I would like to do is, instead of having to do a printf like that, I would like to do something to write a function that allows me to display one of those nodes. So let's go back to the whiteboard real quick. When you have a pointer to one of those struct, okay, we can actually use that pointer to display just the information about this one node, or we can go ahead and write the function so that it displays the information about the node that is pointed to, and then check the next pointer, and if the next pointer is not null, then automatically go to the next node and display also its value, check the next pointer, go to the next node, display its value, and only when the next pointer is null, it's going to stop. So let's do that. Let's implement this function. This is going to be our node underscore display function. So I'm going back to linky.h, okay, and I'm checking real quick the prototype that I have for this. So it doesn't return anything. It's called node underscore display. And it's going to take as parameter. So what I need is I need a node pointer, and I'm going to call that my list. Okay, because it can be a single node, or it can be a node that has actually a pointer next that is not null, and therefore this is the beginning of a list. So okay, this is what I need to implement my function. As we implement over function in this library, we are going to progressively make the move to instead using a pointer on pointer. Okay, and I'm going to call this, well, pointer on list. I'm just going to call it list, okay, but we know it's a pointer on node. Why do we do that? Well, that's one of the differences with the version that's given to you in the reading assignment. This is because eventually some of our functions, not this one, but some of our functions are going to want to be able to take not only the address of the node, but take the address of the pointer to the node. So that P here, okay, in this example. So we want the address of that P simply because some of our functions are going to want to reset the content of that pointer to null, for example. If we deallocate a node, well, we're going to reset that pointer that we were given to null. To be able to reset the pointer to null, you need to give me the address of that pointer right here. Okay? Right here. If you give me the address, then I can manipulate it. So again, in node display, is that super important? Not at all. Node display could be written perfectly fine just using one level of pointer. But what I'm trying to do here is I'm trying to get started with a convention that I will then use for every other function of this library. So whether or not the function actually needs a pointer on pointer, it's going to receive a pointer on pointer. Is that a good idea? Well, it means that when I use this library, I know for sure that the first argument that I always pass to any of my library functions, except obviously not create, okay, is going to be a pointer on the pointer that point to my head for the list. Okay, so it's more a matter of trying to make the library work in a uniform manner so that I don't have to remember that this function wants a pointer on node, but that function wants a pointer on node. I'm putting everybody at the same level. Every function is going to require a pointer on node. Once I get used to it, then it's a no-brainer. Every time I call one of those functions, I give the address of a pointer, I give the address of a pointer. I don't have to think about it anymore, okay? So there's going to be a little bit of initial friction, okay, learning curve. But once we get over that, then you're going to see that it makes it more, convenient to use that linked list library. So this is going to be my header for node display. So now I'm going to save. I'm going to go to linky.c, and I'm going to implement that function. All right, node display. So, like I said, there are two different things that I could do here. I could just display one node. That would be easy. This is like the printf that I was in the main. Or I could make it so that I display the content of one node. So I'm going to use that printf here pretty much. I'm going to cut and paste it. I display the content of one node, and then I ask myself, how is the pointer next inside this node? Is it no? If it's no, then I'm done. Okay, if it's not no, then I need to continue displaying the next element. Okay, and this is interesting because now, based on what we have learned in this course, we have two main design approaches that we can take here. We can go with a loop, so the iterative approach, or we could go with recursion. Since the goal here is to prepare you for the final exam and kind of try to throw in together a lot of the stuff that we studied recently and over the course of the semester anyway, we're going to do both. We're going to do both so that you can see, compare, and contrast and be ready to use either iterative or recursive approaches when the final comes. That's why I have two files here called linky-iterative and linky-recursive. When I have a function for the linky linked list library, when I have a function for this library that can only be implemented in one way, like for example node create, I'm going to put it in linky.c. But when I have a function that could be implemented iteratively or recursively, what I'm going to do is I'm going to take the code, and instead of putting it in linky.c, I'm going to put it in linky-iterative.c, sorry, or linky-recursive.c. Okay, and of course, I'm going to have to include linky.h. There we go. And I'll probably have to include some other stuff here depending on what I'm using, like for example, stdio and stuff like that. So I'm going to actually go here, and I'm going to say that when you include linky.h for the benefit of linky iterative and linky recursive, I'm going to say that when you include linky.h, you should include also stdlib.h for things like null, malloc, and include stdio.h. So when I do an include of linky.h from the main, this is kind of overkill, okay? But when I do it for linky interactive and linky recursive, yes, that's going to make me make my code a little easier here because I just have to worry about including that file here, okay? So here's a version of display node, and this is going to be the recursive version. I just cut and paste it for now. So for now, there's no difference because I haven't implemented the iteration of the recursion, okay? But I just use them as placeholder. So what would happen if I did something like gcc linky test, linky.c, then linky iterative, then linky recursive. So it would complain about P1 undeclared, blah, blah, blah. So this is okay. This is me forgetting that my parameter here is called list and not P1. So I'm going to fix that real quick. That's not the bug I wanted to show you. This one is not interesting. There we go. Just forgetting a detail. There we go. So let me recompile. Maybe we have a more interesting bug this time. So Star list is a pointer. Did you mean to use the arrow notation? Yes, we can do that. So this is actually me having to fix again a bug that is not what I wanted to show you originally. I want to dereference first the pointer on pointer to get to the pointer. So I have to modify this code quite a bit, okay? And then I use the arrow notation to access the field. And it's going to be the same thing here. There we go. I'm just going to cut and paste it. No point in retyping it. There we are. So I'm going to come back in a second on that, okay? But this is the one that interested me, the error that interested me that I wanted to talk about right now. If I try to compile everything like that together, the linker is going to tell me, well, okay, you have a header for node display that is right here in the .h. It's included in the main file here where our main function lives, no problem. That's going to allow me to call node display here without any issue. It's defined not in linky.c, but in linky iterative.c. Here we are. This is a code for my function. But wait a minute. It's also defined here. So both files compile, okay? Linky iterative and linky recursive are compiled separately, and both of them pass compilation because I fix all of those little details here. But then when I try to link together all of the object files, then I realize that I have two versions of the code for node underscore display. And in this case, the two versions of the code are exactly the same, but if I was, the compiler doesn't care. The compiler say, well, I don't know that they are going to be always the same. There's no reason for you to duplicate code, right? So if one of them adds something different like hello world, then now you realize why it's not okay to have two versions of node display, because they can be and they will be different, okay? And then when I call node display, which one am I supposed to actually execute? That's the problem that is shown here. So that means what? That means that concretely, when we compile this, we are going to choose one. We are going to say, I want to compile, for example, using the iterative implementation. And then I can run this. There we go. It doesn't do anything because I'm not calling the node display, so let me fix that. I'm going to go here, and I'm going to say node underscore display p1. So address of p1, I need to pass a pointer on the list element, the node. There we go. Let's compile again. So I can choose to compile linky test with linky c and linky iterative.c. And then when I run it, it displays the node. So it uses this version of the function. And I'm going to leave that hello world here, even though it's really not serving any super useful purpose, but just so that you see the difference when I want to use the recursive version of my function. Then I just say I'm going to compile linky test with linky.c and linky recursive instead of linky iterative. And when I do that and I run, well, I run the other version of my function. So this way, we are going to have two different compilation commands, depending on whether we want to use the iterative implementation of some of our functions or the recursive implementation of some of our functions, okay? And we are going to place those respectively in linky iterative.c and linky recursive.c. So we use only one at a time when we compile the project, that we run it, and that's the version that gets used. So for now, let's go back to the iterative version. That's the one we're going to get rid of first, okay? So I'm going to, sorry. I'm going to change a little bit the way I display things because I don't want to display the pointer always, but I do want to have some sort of, catchy way of displaying in the console. So I'm going to format my display like this. I just want to display the data that is inside the list, okay? And I want to put square bracket around it and a space so that it's going to show clearly on the screen, the content of each element in the cell, of each cell's content, sorry. And then I want to repeat that. So to repeat that, I'm going to use a pointer here. I'm going to use a pointer on node that I'm going to call P, okay? So it's going to be my temporary pointer here to iterate. I'm going to initialize it to null. And I'm going to say actually that P is going to be equal to, so I'm not going to initialize it to learn because I know exactly what I want it to be equal to. It's going to be equal to star list. So remember, we pass a pointer on a node element. That's what I call my list. So now I want a pointer on the node. So I dereference one time, and this is what I get. Now the deal is, I'm going to check first thing, okay? If P is different than null, then I know that you didn't give me a pointer, you didn't give me as argument the address of a pointer that contains null. Okay, that could happen. I could have, like in my main somewhere here, let's go back to the drawing board. I could have in the main somewhere here a pointer, let's call it P3. Okay, so I'm going to put P3 here. If I use a pen, this is better. I could have a pointer P3 that contains null. Okay, if you give me the address of that pointer as argument to my node display, well, there's nothing to display, right? There's no element that is referred to here by this pointer, so I should not display anything at all. That's why I start by checking, if P is different than null, then we are going to iterate. How do I iterate? Well, I'm going to use a while loop. Okay, I could use something different, but I'm going to say while P is actually not null, so while P is true, I'm going to do two things. I'm going to first print the information. So I don't want to go always list because list is the first element only. I want to use P, okay? And since P is a pointer on node and not a pointer on node, then I can remove one level of indirection. So I'm displaying here P arrow data. And then I'm going to advance to the next element in the linked list by saying P equal P arrow next. And if that P arrow next, is equal to null, no worry. I'm going to detect that when I loop back here to the beginning of the loop and test the condition again. If it's not equal to null, then I'm going to use it to display the data that is in that node, and then I will go to the next one. There's one more thing I should really be doing here. Here are dereference list. And nobody should ever call not display and give me a null. You always need to give me the address of a pointer to a node element. So you should give me a valid address of a valid pointer, and maybe that pointer contains null. We just covered that case, right? But you should never give me null to this function. But it's not because I don't want people to call my function with a null that they are going to necessarily do it. If they try to do that, then it's going to crash my code because I'm trying to dereference a null pointer here. So I'm going to add one layer of safety, one layer of security. Before to do this, I'm going to say if not list, or I should say if list equal null, okay, whatever you're most comfortable with, then I'm going to return. I'm not doing anything. I'm not displaying anything because you gave me a null pointer. I should actually raise an error, etc. We're not going to go into that. But the bottom line is at least I don't want to try to dereference it. If list is not null, then naturally I'm going to end up on this line. I'm going to dereference it, get the address of the node, put it in a pointer P. Then I'm going to use that pointer P to iterate and find my way through all the elements of the linked list. Well, this should work with any linked list of any size. But let's see if it still works, on one element, because it should also work on a single element. So when I say not display address of P1, I should be able to display here the linked list P1. And I'm going to add one more thing here, actually. It's optional, okay? I don't have to really worry about that right now. But just for the sake of when I display things, I want to put a printf or a put s, like this, just so that there is a new line, so that I have some spacing. I don't have my shell prompt, right after my display. So let's save this. Go back here. So right now we are just using the iterative version. So there you go. This is a command line I need to use. To few argument to function put s. So okay, never mind. We're going to just do a printf /n. There we go, so that I can add stuff if I want to easily. compile again, it's compiling, and then a.out, there we go. So this is my linked list. What I have right now, again, if I go to the whiteboard, okay, I'm going to select all of this. And we are going to remove it. Oh, there's a piece left. All right. So what we have right now in our main, we have P1. P1 is a pointer on a node, potentially. P1 is equal to null originally. Then on line 11, we call node create. So node create allocates dynamically one of those structure. Okay, there we go. It puts the value 42 inside the data field data, and it puts the value null inside the data field next. And then it returns to me the address, which I assign to P1. So this is what I have after execution of line 11. Line 12 is given the address of P1. Okay, so let's say P1 leaves that memory address, I don't know, alpha. Okay, so I pass alpha to not display. Not display dereference that, find P1, check if P1, first check if the value that I gave is not null, then find P1, check if P1 contains nulls. If it contains nulls, it doesn't do anything. Since it doesn't contain null, we enter the loop. We display 42 on the screen. So there we go, this is what we display. And then we do the same job, this time with our pointer P inside the function, pointing to, so initially P points to this, okay, and then P points to the same value that is here, which is null. And then this is when I know that I am done iterating over my list, okay? All right, so that's what we have so far, but we have tested our function to display an entire linked list. We tested it only with one element, so that's going to be a problem. And we also only implemented, we only implemented the iterative version. So before to move forward, let's get rid of that node display function. Let's get rid of both versions, iterative and recursive. So we have the iterative version here already. Let me jump to Linky recursive. And we are going to be able to use some of the stuff, okay? There's some of the stuff that's going to be common, like for example, if you give me a null, definitely I don't want to do anything, okay? So I'm going to just return. After that, we are going to see, okay? So this one allows me like some safety, like I already mentioned. Then we are at the core of the iteration. So at the core of the iteration, somewhere I'm going to do this. I might have to change the way that I write, P, etc. But I'm going to do this. I'm going to try to display the data. So given that I am passed here a pointer on a node, okay, I'm going to use that pointer on node, and I'm going to say, okay, first dereference to get the pointer itself, and then when I get the content of the pointer, then use the arrow notation to access the field inside the node, the field data inside the node that is being pointed to. So if I write this, I'm assuming that list is not null. So you gave me the address of a pointer. And I'm assuming also that this pointer doesn't contain null. If that pointer contained null, then star list would be null, and star list arrow data would cause a crash. So I need to ensure that this is true. So I'm going to say if star list, okay? So if the pointer which address you gave me contains something that is not null, so I could write it star list different than null, so on and so forth, okay? Then what I'm going to do is I'm going to use that pointer to display what's in the current node. Very well. And then how do I recursively repeat myself? How do I iterate recursively? Okay, I need to call the function. So I need to call node display. Because right now I displayed the node that was pointed at by star list, but I want to go to the next one. So I want to call myself recursively, and I want to say, okay, now display the rest of the linked list. The rest of the linked list, well, the head of the rest of the linked list is whatever is pointed to by next. How do I access the next field? Star list, a row, next. If I write this, I'm giving you the value of this pointer. Let me show you on an example here real quick. So I'm going to have to clean up a little bit first. There we go. Remove all of this. Remove this as well. Okay. So let's say that I don't have actually, I don't have only one element here. I'm going to say that I have at least 2 nodes in my linked list. Okay? So I'm going to represent this like this. I have a pointer here that points to the linked list, to the next linked list element that contains, for example, 23. And we're going to say that this one has a next pointer that is equal to null. Okay? So this is a situation in the main. In the main, I have this P1 pointer, okay, that is pointing to a node. And let's say that I found a way to attach a second node. So it's not done yet in the main, but we're going to work on that next. But let's say that I found a way to attach a second node here. Now what I'm doing is I'm calling node display with the address of P1, so alpha. And inside of node display recursive, what I'm going to do is I'm going to first check that alpha is not null. This is okay. Okay. So list contains alpha. Okay, alpha is not null. So line 4 is happy. Line 6 is going to say, okay, now let me dereference list. So I dereference list and I find what is located at memory address alpha, which is a pointer P1. And I'm asking, does that pointer contain null? Well, no, P1 points to the first node of my linked list. So again, line 6 is going to be true as well. And now what I do is when I do star list arrow data, okay, what I'm doing is I dereference from list, so from here, okay, I dereference, so star list is actually what's inside P1. P1 arrow data, that's 42. That's what's right there. Okay, so this is how I figured my way, and you can go back to the module that introduced structures and pointers on structures to see that this kind of diagram is really gold to make sure that you know what to write here. But now when I call node display wants a pointer on a pointer on a node. Okay, this here, just like this. These things are of data type pointer on node. So this code here, star list arrow next, gives me the address of a node. But I don't want the address of a node as argument. I want the address of a pointer to a node. So I need to put the ampersand sign in front of that. That means that when I call myself recursively, right? When I call myself from the main, I get the address of P1. When I call myself recursively, let's say that this pointer next here is at address beta. I call recursively node display, and I give as my argument beta. Okay, so now inside, let me remove this. Now inside the function, there's no longer going to be an alpha here, there's going to be a beta. That means that the list in that recursive call is going to point to actually this pointer right here. And I'm going to apply the same logic. Star list means the pointer that is inside the first structure. Star list arrow data is going to give me access to the field here that contains the value 23. Okay, so that's the important thing to understand about how we use linked list here. And yes, it makes actually the notation a little bit more complex, but this is exactly what you want for a review. If you want to make sure that you understand, how to dereference and take the address of pointer and use pointers on pointers, this is the kind of code you need to look at. So this is why we use it in this version of our linked list. Okay. We push a little bit harder so that we make sure that everybody is ready for the final. So let's try to compile this. So I was compiling with Linky iterative. Now I'm going to save Linky recursive, and I'm going to be lazy and search for the command line. There we go. So now I'm compiling the version with Linky recursive, and when I call it, well, of course it does the same thing, because my list has still only one element, but it does it this time recursively. All right. So to sum up, we have linky.h, we have linky.c, we have pretty much everything set up for the rest of those videos, okay? The separation between the iterative version, the recursive version. The only thing that we didn't really do is we limited ourselves to creating one standalone node and display it. Now the next step is going to be for us to make it so that we have functions that allow us to combine nodes together, attach them one at the end of the other to have a linked list of more than one node. And we are going to, because we have already that function readily available, we are going to use node display to debug, to make sure to test, to make sure that as we say, for example, I want to add the value 23 at the end of my list that contains 42 right now, then when I display the whole list, I still get 4223. Or if I add 23 at the front of the list, then I get 2342. We are going to save that for the next video because this one is getting a little long already. So I'm going to wrap up for this video here. As usual, please make sure you don't jump to the next video before to understand this one, and use forum, Piazza, whatever we're using this semester, to ask your question, or even better, drop by during office hours. And I'll see you in a few minutes in the next video.